Okay, so in general, it's not going to be the case that our differential equation has this special format of a derivative times some function plus y times the derivative of that function equals whatever the right-hand side is. In general, we won't see that. So for example, below we have this standard format linear DE, y prime plus 3y equals 4. Okay. Leibniz, one of the inventors of calculus, had the really good idea that we could be very careful about choosing a function. We could specifically pick out a function that we could multiply both sides of this equation by, so that it has this nice desirable form where the left-hand side looks like the derivative of y times mu. Okay, so why don't we take a moment and we'll look at what we could multiply through by. I'm going to say, let's try multiplying both sides here by some function. I'm just going to write mu. So I'm going to multiply both sides here by some unknown function mu. Okay, that we're going to guess. Okay. So this is looking a little bit closer to that format that we had here. If we knew that 3 mu was actually equal to the derivative of mu, then this dE would be y prime mu plus y mu prime equals 4 mu. And our left-hand side would look like the derivative of a product. So we could undo that differentiation with an integration and solve for y. All right, so here is where we're going to put our energy in. We would like to think of a function where the derivative of that function is 3 times the original. Now, we've been working with exponentials quite a lot, so we're going to try that out. What if mu equals e to the 3t? Notice that our derivative is 3e to the 3t. And so we satisfy this condition. Okay. So this function is called an integrating factor. Okay. We'll talk about how we choose it in just a few minutes. Okay. So what we're going to do is take this function e to the 3t. We're going to multiply both sides of the equation by e to the 3t. So we have y prime e to the 3t plus 3e to the 3t. That's the derivative times y equals 4e to the 3t. Okay. Now, this is the derivative of e to the 3t. And so we see that this left-hand side, we have that turn taking for differentiation. And so our left-hand side is just the derivative of y e to the 3t. And so if we're interested in finding y, we can get rid of this derivative by integrating both sides. Okay, so we can integrate the derivative of y e to the 3t. That one is easy because the integral just undoes that derivative. And this gives us y e to the 3t on the left-hand side. To do the integral on the right, we're just going to do a little u substitution. U is equal to 3t. Du is 3 dt. So 1/3 du is dt. This is going to be the integral of 4/3 e to the u du. So it'll be 4/3 e to the u plus c, or 4/3 e to the 3t plus c. All right, now we had y e to the 3t equals 4/3 e to the 3t plus c. We're interested in finding y, so we're going to divide both sides, everything on both sides, by e to the 3t. So we get that y is equal to 4/3 plus c over e to the 3t. We can leave it in this form or rewrite it as y equals 4/3 plus c e to the negative 3t. And we've done it.